In my previous lectures, I talked about the distinction between the caloric theory of heat and the mechanical or kinetic theory of heat, and how the caloric theory of heat saw heat as a substance that was indestructible and moved from one material into another, causing its temperature to rise when it entered and to fall when it leaves. The kinetic or mechanical theory of heat, on the other hand, which was articulated by people like Maxwell and Clausius and Kelvin and Helmholtz, stated that heat is really just a form of molecular motion. One of the central players in the kinetic theory of heat that ended up developing significant advances in the kinetic theory of heat was a man named James Joule. Helmholtz talks about him on the bottom of page 127 of A Student's Guide to the Great Physics Texts. James Joule did a number of famous experiments on the mechanical theory of heat. The question he was interested in was how much heat can be generated using a given amount of work. Remember now, the idea is that work, specifically forces in motion, can produce heat. And conversely, heat can produce work. So the question naturally arises, how much work is required to generate a unit of heat? Well, first thing we need to do is explain what we mean by a unit of heat if we're trying to be quantitative about this. So what is a unit of heat? There are many different units of heat that could be used, but the one that we are going to adopt, or rather that Helmholtz adopts, is the following. The unit of heat, so 1 unit of heat, this is the question, 1 unit of heat is equal to the amount of heat required to raise 1 gram of water by 1 degree Celsius. So notice that this assumes that we know what the Celsius temperature scale and we know what 1 gram is. So that's how we will define 1 unit of heat. That's how Joule defines a unit of heat. So the question is, how much work is required in order to generate such a unit of heat? Well, I'll jump right to the answer that Joule provided. He said the amount of work that's required is the same amount of work that is required to raise 1 gram weight by 425 meters. So it's equivalent to, let me go right this way, the work required to accomplish or to deliver 1 unit of heat is the same work required to lift a 1 gram mass 425 meters. Now that's quite a height. That's almost half of a kilometer. So we could figure out how much work that is. Well, the work would be equal to the weight times the distance, right? That's how we compute work. And the weight would be, well, 1 gram is 0.001 kilograms. And if we want to convert that into a weight in newtons, we'd have to multiply by 9.8 meters per second squared. That's a conversion factor. I'm just going to round off to 10 meters per second squared, and I won't be too far off. And multiply that by 425 meters. And you'll see right away that, well, this becomes 0.0001 times 10 times 425. That gives us 4.25 Newton meters, or 4.25 joules. That is the amount of work one needs to do in order to deliver or to create 1 unit of heat. That is the amount of work required to raise 1 gram of water by 1 degree Celsius. Now, this is kind of abstract. It's 4.25 joules. You don't really have a sense of how much this is, but maybe to give you a sense of this, suppose I were to take a 1 gram cube of water. So this is 1 gram cube of water, and you want to know how much heat you have to put into it. The heat you have to put into it, I'll call that Q for heat, put into it to raise by 1 degree Celsius. Well, the same amount that it would require if you were to instead take this 1 gram of water and drop it off the top of a building. And as it's falling, it's losing that potential energy, it's gaining kinetic energy. And if it falls 425 meters, all the while it's gaining speed faster and faster and faster and faster. So this is, water inside of here. It falls 425 meters until finally it lands below on the pavement, and if it's in some little container so that it doesn't splash everywhere. All that kinetic energy that it had acquired, if that was all turned into heat, this would go up. It would be just enough heat to raise it by 1 degree Celsius. So if you think about it that way, it seems like it requires quite a bit of energy to raise 1 gram of water by 1 degree Celsius. And the reason why this is actually is because water has a fairly high heat capacity. It can actually store a lot of heat before it goes up by 1 degree Celsius. Okay, but that's just to give you maybe a little bit of a common sense notion of what we mean by what we've been talking about. Now, how did Joule measure this quantity of heat required to raise 1 gram of water by 1 degree Celsius? Well, he set up an experimental apparatus. I'll try to make a sketch of it right here. So he essentially took a pulley, and this pulley he put a rope over it, and he hung from this rope a mass. I don't know what mass he used, but some weight right here. And then this rope he wrapped around. There's several ways that he did this experiment, so I'm kind of explaining one of the ways he did the experiment. He wrapped this rope around a shaft. So I'll draw the shaft right here. And this shaft he had attached to some fins, and these fins were inserted into a bucket full of water. So I'll draw the bucket first, like this. And I'll put some water in here. Okay, and let me continue drawing this shaft going down into here. I'll kind of draw what's going on inside of here. He had these fins attached to it. Imagine it looking a bit like this. I'll go ahead and draw the solid lines. This is roughly what's going on. And so as this weight was allowed to fall, what would happen is that this shaft would rotate as it fell. So this shaft would rotate around in this direction as it fell, and these fins would then, of course, spin around, and they would churn the water. And while they were churning the water would heat up a bit. Not much, but it would heat up a little bit. And if you then put a thermometer in the water, you could measure what the temperature rise of the water would be. So you might imagine this is a mercury-filled thermometer, or maybe an alcohol-filled thermometer, and you measure the temperature of the water. So let me label a couple of these things. This is the thermometer right here. This is the falling mass right here. This is the water right here. And so what one can do then is see how far this falling mass has to fall in order to raise the temperature of the water by 1 degree Celsius. And of course, as the mass falls, it is doing work, and the amount of work that it's accomplishing can be written in terms of the distance of fall. And this is precisely how we arrive at this relationship between the work done and the unit of heat. This is what Joule did, and this is what Helmholtz explains in this chapter.